brief note about myself. My name is Gary Wolff. I work for OTAC in our Portland office, and my real role at OTAC is I'm a senior hydraulic engineer, and I basically work on a lot of our Portland projects, but I actually support the company throughout all our different offices on hydraulic modeling and hydraulic design, that kind of stuff. So the presentation I'm going to give here is right in my sweet spot. It's going to show you guys some hydraulic analysis and hydraulic design of this road crossing for Lane County. So I would like to acknowledge Lane County for this very fun project for us. The county, Kerry Warner and his team there at Public Works are really fun to work with. And as you'll see in some of these slides, this was really a beautiful setting to work. So with that, let's get started here with the presentation. So hang on a second, I've got an annoying thing there. Okay, so just an outline of what I'm gonna hope to talk about today. So this is gonna be really a case study of a project we did with Lane County. This is the hydraulic design of the Territorial Highway where it crosses Coyote Creek. But really what I hope to get in this, or do in this presentation for you folks that may not be real familiar with the hydraulic design of bridge crossings, hope to give you an introduction of how we go about doing that. So that is basically the outline I have here. I'm gonna start out giving you a little introduction to the project and give an overview of the hydraulic design approach for projects like this. And then we'll basically just step through that process, talking about channel stability and our site investigations, doing the hydrology. And then really a lot of the talk will be about hydraulic modeling. And in particular, I'm going to talk about the two-dimensional hydraulic modeling that we did for this fairly complicated stream crossing. So that's something that's becoming a lot more prevalent in our industry, and I want to give an introduction to that. And then I'll just finish out talking about the scour analysis of there's two bridge crossings here, and talk about how all that fits together in our design recommendations. Let me see here. It's not advancing. There it goes. Okay. So start out with an introduction and an overview of the design approach. So what we're talking about here is the Territorial Highway here southwest of Eugene in Lane County. Basically, this highway was recently, the ownership of this highway was recently acquired by Lane County from the state. And as part of that acquisition, the state did give the county some money to do some upgrades on this road. This is a really beautiful area. There's actually, I think there's a famous winery out here, the King Estates Winery. It's also a very popular road for recreation, like bicyclists from Eugene, et cetera. So the county really wants to make some improvements to this road corridor here. And what we're going to be focusing on today is where the road crosses Coyote Creek. So here's a blow up of that area. So just a quick overview of this area. We've got Coyote Creek here. We got this really wide floodplain. This is just south of an area known as Gillespie Corners, if you've ever been out there. And we got two branches of the creek that come together here and then flow across this road. And so what the county wants to do, they want to, this road fairly frequently floods every few years. And they want to, as part of this highway improvement project, they want to get this road up out of the flooding. And so that's where we help them with the hydraulic design of that. How can they raise the road and meet all their design goals for that part of the project? So that's what I'll be talking about as we go through this. So first, let me just give a quick overview. When I talk about bridge hydraulic design, I want to just kind of talk to you about what we're trying to do and what information we're providing the design process. So here's what we're trying to do with the hydraulics. First of all, we're helping the project understand how big is the opening need to be to adequately pass the design flows and any other things like debris. So that providing an adequate waterway opening for the stream. And as part of that, we want to, of course, build a bridge and a highway crossing that doesn't increase flooding. And this often comes into play when you're doing like floodplain permitting. Of course, you're probably familiar with the no-rise analysis. And then our hydraulics also feed into the scour, computing how much erosion there might be around the bridge foundation and that'll help with the bridge team in designing the foundation. And then as part of that, you know, we're often designing scour countermeasures, bank protection, those kinds of things. And then we also want to understand, you know, there's a impact of the waterway on the highway or the bridge, but there's also an effect on the bridge on the stream. So we want to understand that interaction, make sure that what we're doing is also keeping a healthy stream. It's also healthy for stability as well as for other environmental considerations, for example, fish passage. So we're interacting with the permitting process as well. So this is just an overview of the basic steps that we go through when we're doing a hydraulic bridge design. We start out by gathering background information on the project. If there's an existing bridge, we're looking at bridge inspection reports, geotechnical reports, FEMA flood insurance studies, that kind of stuff. And then we're getting out in the field because it's really important to understand on ground what's going on. And this was actually a really fun part of this project because it was such a beautiful area. So it was really fun for us to get out there and see what was going on. Tied to that site visit is a geomorphic assessment. So what we're trying to do is understand the stability of the stream, what the stream processes are, and how that's going to interact with our proposed bridge. Then of course, we have to have hydrology. We have to have design flows for the project. So we do our hydrology to figure out the design flows. Then we get into the hydraulic modeling, which is really the meat of the hydraulic design process. So I'm going to talk in some depth about that today and also get into the two-dimensional modeling, which was a pretty exciting part of this project. So once we've got the modeling going, then that feeds into the rest of the design process. We do scour analyses to understand what the erosion might be around the bridge foundation. And then we can help the design team with recommending scour countermeasures to limit that erosion. And then the hydraulics also fit into the environmental permitting process. So moving on here, let's talk a little bit about channel stability. It's something that's really important that you understand the behavior of the stream and how that's going to interact with the bridge or bridges you're designing. So really, I like to think of this as three main questions that we want to address when we're thinking about the stability of the stream. First of all, what is the lateral or planform stability of the stream in the vicinity of the structure? So, you know, as you know, rivers move around naturally. So if you've got a stream that's meandering and that, you know, even it might be a natural process where the river is meandering and moving, we need to understand that so that we make appropriate design decisions at the bridge that doesn't cause problems for the structure now or in the future. We also need to understand what's happening vertically with the stream bed. So if the stream is eroding down, like is very common in a lot of streams, particularly in urban settings where there's been a watershed change or something where the channel is wanting to lower down, we need to understand that because that's going to affect our bridge foundation. And finally, related to lateral stability, we want to understand, you know, what are the local bank erosion problems right at the structure itself. And we want to be able to address those as part of the design. So we start this understanding of stream stability by doing a detailed field reconnaissance. And so as part of that, we want to understand the general characteristics of the stream at the crossing. You know, what are the hydraulic controls for our hydraulic analysis, things like riffles in the stream or any other hydraulic features in the general area. We're looking at the stability of the stream, both laterally and vertically, because we need to understand that and actually make potentially some quantitative predictions of that for the project design. If there's an existing bridge, we're looking for existing scour problems that we hope to address as part of the project. We're looking at channel and floodplain roughness for our modeling, understanding bed and bank material characteristics that will feed into our analysis. And often what's a really important part of this is the hydraulic engineers are really assessing what the survey needs are for the project and working with the surveyors to make sure that we get the right geometric description of the stream in the vicinity of the bridge. So this is now Coyote Creek here at the Territorial Highway. So this is the existing highway here that crosses this very wide floodplain. It's about 1,500 feet wide. You can see the stream here. This is the main corridor of the stream coming down here. This is the South Fork. There's another channel that comes in here from the North Fork. These join right here and then pass through one of two structures at the road crossing. There's two bridges here. There's the North Bridge and the South Bridge. So what's going on here, we've got the roadway, which is it's raised up above this very wide floodplain, and there's two openings here by these two bridges that can pass flows through the road. And what happens in a big flood, you have flood waters that come in here and inundate the whole floodplain, and it passes through here. Well, these two structures aren't big enough for the really large floods, so the road is overtopping, and that's what the county wants to address as part of this project. They want to raise this road up, and of course in doing so they're increasing this sort of dam you can think of across the floodplain. So we helped the county figure out how to provide enough conveyance through that raised road that we would meet the design objectives. Okay. This is a very unnatural condition here. So this stream was straightened back in the past, probably when they came in here to farm this area, to drain what was maybe wetlands in the past. So that all ties into our understanding of the history of the stream and what the stability is going to be for our project. So I'm just going to show some photos to illustrate what's going on, and you can see what a really nice setting this was and why we liked working on this. This is just the road here crossing the floodplain that's looking north, from the north of the two of those bridges there, towards what's the geographic thing there is what they call Gillespie Corners back in the background there. This is the roadway looking south across the floodplain. So you got this road that's a little hard to tell in this photo, but it is raised up above the adjacent floodplain, and you got those two pretty much grade bridges on the roadway. This is doesn't show much, but this is actually looking from the North Bridge at the main channel, looking north, and you really can't hardly see the channel there because the vegetation is so dense. So this little stream's got a lot of hydraulic roughness, particularly upstream of the bridge. That's the same stream now downstream of the bridge. There's a little more opening there. You can see the channel. So we're looking at that and then trying to understand the hydraulic characteristics of that stream. So this is the existing North Bridge crossing of the main channel there, and you can see that while this is about a 60-foot span across the channel, it's that the stream isn't seeing the full opening there because there's been some slumping or something in the past that's obstructing the inlet to the bridge. So part of our design was to try to open this up to get better conveyance through that opening there. And this is just a view on the other side, the downstream side of that North Bridge. There's also construction there as well. And again, this is that very densely vegetated channel just upstream of the North Bridge. A lot of vegetation there, and not a lot of hydraulic capacity because of all that vegetation and stuff. So this is a view now looking down towards the road in the South Bridge. So what you have here, and I'll just go back some slides, right there. So you have this wide floodplain. So historically, there were probably two channels that came through here. So this is now somewhat of an overflow channel. So this does engage in large floods, but when they channelized this back in the day, this became more of the main channel. But during large floods, you still get flow across this wooded floodplain here and into the South Bridge. I'll give you some context there. So that's what we're looking at there, down towards the South Bridge. There was some clearing that was done here, so it was a little rougher than that before that clearing. And this is the opening at the South Bridge. So it is a little bit constricted there, but that's kind of, you think of this as sort of an overflow bridge for large floods. This is immediately downstream of the South Bridge. So while there's a bit of a swale or remnant channel across the floodplain upstream of the bridge. When the water goes under the south bridge, it runs into a wall of vegetation and high ground. So really, there's not much capacity there. And that's part of our project, was to improve that conveyance there at the south bridge. Okay, so let's think about what we have to learn here and what we have to quantify for the bridge design. So let's talk about the lateral stability of the stream. So this channel is what we call incised. It has eroded down over time. That's evidenced by the steep eroding banks along there. However, there's little evidence that this channel is migrating laterally. So we've looked at aerial photographs and we had our field observation. The channel is pretty much right. That north channel has really stayed right where it is over time. So the lesson there is we don't see any lateral instability that's going to be a threat to our new project here. So there might be some local bank erosion that we may want to address right in the vicinity of the bridge, but this channel, it doesn't appear to be meandering in the way that's going to be a threat to the project. And likewise, the south bridge, there really is no active channel upstream. This is just remnant overflow during large floods, so there's no stability problems there that we have to worry about either. And then the other thing we need to really quantify is the vertical stability. And what I'm talking about here is, if you look at the stream overall, is it going to continue to erode down that would then potentially be a threat to the bridge foundation over the life of the bridge? So while this is an incised channel and it has seen past erosion, we believe, currently it's a very low gradient stream. It's meandering, particularly downstream of the bridge, and there are beaver dams in there. We've looked at the bridge soundings from bridge inspection reports. We don't see any systematic changes going on there. So our conclusion is that while there's been some degradation in the past, currently this channel doesn't appear to be cutting down vertically. So we don't feel that's going to be a threat to the road crossing over the proposed design life of this bridge. And that's going to come into play. I'll show you guys that when we get to the scour calculations. That'll be one of the components of the scour that we're going to quantify. Just the existing bridge scour, there is evidence of what we call contraction scour at both bridges. You may have seen that in the photographs. It's kind of scooped out. The channel bed is actually lower under both of those bridges than the channel adjacent to the bridge immediately upstream and downstream. The current bridge foundation, these are vertical concrete walls that actually are founded on pilings. So the bottom of those walls, or the bottom of the pile caps, currently are not exposed. At the walls themselves on the north bridge, they look like they're about 6 to 8 feet above the bottom of the walls, about 6 to 8 feet below the local ground elevations, or about 3 feet below the channel invert. The south bridge is a little shallower. It's about 2 feet below local ground elevations, and maybe only about 4/10 of a foot below the channel invert. So any additional erosion or scour that would expose the bottom of those walls would cause the bridge to be what the Federal Highway Administration calls scour critical. And actually, both of these bridges have a scour critical rating. There was a quantitative analysis of these bridges done many years ago where they did what I'm going to show you. They did a hydraulic analysis and computed the potential scour during a large flood that showed potential exposure of the pilings. And that's why these bridges have a scour critical rating, and something we want to address as part of this project. So, okay, so that's an overview of channel stability. Let's move on now to the hydraulic design process. First, we'll talk about the hydrology, the design flows. And so when you talk about design flows, there are several different things we want to think about. First of all, when we want to figure out what kind of a bridge capacity we want to achieve with our project. And in consultation with the county and working through this project, we decided we could get to a 100-year design level for this project. In other words, the goal was to pass the 100-year flood without the road overtopping. For bridge scour, the design discharges are kind of mandated by ODOT and the Federal Highway Administration for a safe bridge crossing. You design for what the 100-year event, that's sort of your bridge scour design event, and then you check it for what they call the check discharge. So you compute the scour for both. And in the check discharge is really the discharge that in theory will give the sort of the worst case scour condition. And that sometimes can be when the road is just starting to overtop. That would be the worst case scour. Or if all the flow goes under the road, even up to the 500-year event, the 500-year event is considered the check discharge. And then finally, for floodplain regulations, you probably know it's the 100-year event is the magic flow that we have to look at. So how did we do the hydrology? Well, unfortunately, there were no stream gauges anywhere near this road crossing. There was one way downstream on Coyote Creek, down close to its bottom of its watershed, but it was too far away really to be of a whole lot of use for this project. We did analyze the flows down there, but in the end, what we ended up doing was using, you may be familiar with StreamStats. So this is StreamStats is actually a program managed by the USGS, but what it's based on are what are known as regional regression equations. So what the USGS does systematically across the whole United States, they analyze flow records at gauge stations, and they correlate, they do flood frequency analyses of those gauge records, and then correlate the computed peak flows with basin characteristics at each gauging station, and then develop equations that relate the peak flows to watershed characteristics. And that's what's known as a regional regression analysis, and what comes out of the StreamStats. So we just use StreamStats here. And here's the result of that. So at our bridge crossing, which by the way has a watershed area of about 24 square miles, you know, for example, we come up with about 2,900 CFS for the 100-year flood. As you'll see when we get into the hydraulic modeling, we needed to know the flow actually at both branches upstream of that. So we ran StreamStats on each one of those and basically prorated the flows based on those results so that the total of the North Fork plus the South Fork equals the 100-year flow or at the bridge itself. So anyhow, these are our design flows for this project. So moving on now, I want to get into really the heart of the discussion today, which is the hydraulic analysis and the hydraulic modeling, because that forms the backbone of our hydraulic design. So when I'm doing modeling and when I tell folks that are learning about this early in their careers, I always tell them, think about what answers you want to get out of your analysis. So these are the kinds of things that we want to learn by running a hydraulic model. First of all, it's going to form the quantitative basis of our hydraulic design. So that means that, the modeling is going to help us evaluate what is that capacity. Are we passing that 100-year flood? So the modeling is going to help with that. It's also going to evaluate flooding and impacts on flood elevation. So it helps with our floodplain permitting and evaluation of flooding. Then the hydraulic modeling results then, things like velocities and depths and shear stresses, then go into the hydraulic design, things like calculating the scour depths, figuring out how big the riprap needs to be, those kinds of things. And then it also can play in a role in things like environmental permitting, like if you have to meet fish passage requirements, the hydraulic modeling often becomes a part of that process as well. And it also helps us to make sure that what we're doing isn't having a negative effect on the overall stream health and the stability of the stream. So that's what we're trying. Those are when you're doing the modeling, those are the things you want to be thinking about. So many of you probably are familiar, if you've done bridge projects, the normal way we do bridge hydraulics is what's called a one-dimensional hydraulic model. This is the HEC-RAS that you probably are maybe very familiar with. This is a one-dimensional model It's actually a steady state model, which means, or mostly it's done in steady state, which means that things aren't changing in time. And it's based on what's known as the energy equation. And if you've, for the civil engineers that have gone through an open channel flow course, that's the standard step backwater method is what it's doing there. Bottom line is, what you get out of a one-dimensional hydraulic model is you got a series of cross sections up and down your stream, and the model computes a water surface elevation at each one of those for a known discharge, okay? So you have a single water surface at each discharge, and once you know the water surface, then you know the flow area, you know the discharge, you basically can calculate a velocity. So it computes the water surface, and then you get these average results based on that water surface. You get a depth, you get an average velocity, and an average shear stress. So really, you're just getting an average result at each cross section. The model doesn't explicitly tell you what's going on across the, the cross section, like what's happening in the channel versus the floodplain. The model will tell you some things like the average velocity in the channel versus the average velocity or flow in the floodplains, but that's an approximate result. It's not inherently part of the physics that go into a one-dimensional description of the flow. So there's just a whole lot missing in that analysis. While this works well for a lot of streams, the assumptions that go into this sometimes can be a problem on more complex waterways. And so really the big things that are missing here is we don't see any, with a one-dimensional model, we don't see anything that's going on transverse to the flow. So things like transverse velocity variations or variations in the water surface elevation. We're assuming a constant water surface, variations in the energy grade. And the flow doesn't know what's going on internally to the flow. So there's no momentum exchange between fast-moving water and slow-moving water. It's all sort of one stream tube, if you will. So, so what I want to talk about now is where that really can become a problem when we're doing something like a hydraulic bridge design. So if you got a bridge across a really wide floodplain with things like, a really wide floodplain, and maybe there's multiple bridge openings in that waterway, the road may be really skewed to the flow, maybe have multiple channels, or maybe you're in a large tidal waterway. All these scenarios lead to where those one-dimensional assumptions really start to become pretty weak, and we need a better tool for those kind of scenarios. Well, luckily, we have now two-dimensional modeling. Two-dimensional modeling has actually been around for a while. It's been around actually most of my 40-year career, actually, but the modeling tools have historically been very cumbersome to use, and the data requirements for running those more complicated 2D models historically have been expensive, and the models were very unstable and just very expensive and difficult to use. So they've been around for a while, and they've been used on projects for quite a long time, but they weren't part of common engineering practice. Well, really, that has rapidly changed in the last few years. We have much better tools. One of the main things is the hydraulic models now are a lot more stable. So just getting the models to give you an answer is a lot easier. They're just becoming a lot more common that way. And we also have the data to run the models are getting less expensive and easier to access. We now have LiDAR for the terrain, which really helps. So what I'm gonna make a case here is two-dimensional modeling is really becoming a lot more mainstream for projects like this. And you're gonna see that a lot more in the future because the models are so much easier to use. And I'll even make a case that there are a lot of situations, even like the one I'm presenting here, where setting up the model and running it actually can be easier in two-dimensional than one-dimensional. And you've got rid of all of these assumptions that are sort of highlighted here. The 1D models basically assume the flow is all in one direction, predominantly down the main flow path of the river or stream, doesn't see things laterally to that, where a two-dimensional model actually computes the entire flow field and sees the flow directions and velocities throughout the throughout the modeling domain, both down the river and laterally to the river. So big advancement there. So here's just kind of a comparison between the models. This was actually the Nehalem River out in Tillamook County, a project we did a few years ago. So this is what a one-dimensional model would look like in that scenario. You've got these cross sections that are transects across the channel and floodplain. And what we're doing here, you can see these cross sections aren't straight lines. They have little dog legs in them. The modeler is trying to guess what direction the flow is going, because in a one-dimensional model, you're basically telling the model what direction the flow is by how you lay these cross sections out, because you're going to get a single water surface at every cross section, and the flow needs basically to be perpendicular to that cross section. So you're kind of telling the model where the water's going. Where in a two-dimensional model, what you're doing is you're overlaying a computational grid over the modeling domain, and you're getting a result at every one of these nodes in that grid, and that result is a velocity and a direction at every location and an elevation. So you're getting really a much more complete description of what the flow field is looking like. And the model is figuring out that for you. You're not having to tell the model where the water's going. So that's what we did on this project. So what I'm going to show you is the two-dimensional modeling we did to help Lane County on this really interesting project. The model that we used was the Federal Highway what the Federal Highway Administration is promoting. It's called the SRH-2D model. It runs under the SMS software. Federal Highway Administration and ODOT is really promoting that for projects like this. Another common two-dimensional model that you guys may be hearing a lot about these days is the Army Corps HEC-RAS program now also has two-dimensional modeling. It is somewhat limited, however, because they don't have the bridge routines now built into HEC-RAS. So that, and for other reasons I won't go into right now, the Federal Highways right now is really promoting SRH-2D for hydraulic design of bridges. So to run these 2D models, the big data requirement is that you have to have a complete terrain of the model domain. Okay, so that's maybe a little more onerous than one-dimensional models where we just have cross sections, but honestly, it's really not that much harder to get. Because in this case, what we did is we used high-resolution LiDAR, which you can see here, that all this is LiDAR. The pink are actually cross-sections of the main channel that the county surveyed for us. So we had actually cross-sections of the channel, which the LiDAR unfortunately doesn't pick up very well, doesn't see below water generally, and it does have a hard time if there's really dense vegetation. So we had the main channel picked up, and then they surveyed, of course, the road corridor here really well. So we had all these data sources. These were all combined then to create a continuous terrain model, or a DTM, of this area, which is the geometry that we needed to run our 2D model. So what happens is then you have the terrain, then you overlay the terrain with what's known as a computational mesh. So this shows the domain of the model we built for the Territorial Highway project. This is our road crossing down here, the north bridge there, the south bridge there. And the model domain had to be big enough that we were far enough upstream and downstream of the road that we could, that our boundary conditions, where we have to make assumptions on what the flow conditions are there, aren't having a big influence on what's happening right where we're interested. So in this case, our model has a flow input for each one of the two streams that are coming into the valley here. And then we specify a water surface at the downstream end. This is very much like you would do for a one-dimensional model. So the model, when you specify a water surface, it's computing the flow distribution there. You're giving it the discharge here and here. It's specifying the flow distribution there and there. And then the model works out what's happening in between those boundary conditions. And so we get a complete description of the flow that the model is computing inside that domain. This is just a close-up of the modeling, the computational mesh. It's made up of triangles and rectangles generally, and we have higher density, smaller elements in the vicinity of the bridges because we want more detail in those areas. And then you can make the mesh bigger cells out away from the bridges. So that's what we did here. So you've got your geometry described by the mesh and the terrain. The other big important hydraulic parameter is the hydraulic roughness. You know, you're probably familiar with Manning's N values for a one-dimensional model. We actually use those for two-dimensional modeling as well. They have a slightly different theoretical meaning, but essentially they represent the same thing, hydraulic roughness. So basically for two-dimensional modeling, we have to specify, again, the areal extent of the variations in roughness. So it's just a GIS exercise to go in and delineate basically the different land uses from you know, aerial photography and then the mainstream channels, and then assigning roughness values based on the aerial photography and on, you know, actual field observations. So, very much like one-dimensional modeling, but just with more detail. So that's we've got our terrain, we've got our mesh, we've got our N values. Then we put in those boundary conditions, we put in the flows at the upstream end, the watershed at the downstream end, and we can run the model. And it figures out what's going on. So the next thing I'm going to show you guys real quickly is, you know, when you're doing hydraulic modeling, you ideally like to calibrate. We didn't have detailed calibration information here. There are no stream gauges, so we're estimating the flows, like I said, from stream stats. And with no gauges, we don't have a record of flood levels in this area. So all we have is anecdotal information that this road overtops every few years. And it just so happened that while we were doing this project, or getting going on this project, there was a big flood in April of 2019. Been an unusually wet period for April, but they had what was a pretty big flood that actually almost overtopped the road. You can see that in this photograph here. This is the low spot in the road out here to the north, and it almost overtopped that. So what we did with the anecdotal information, we decided this was probably on the order of a 2-year event. We don't know that precisely, but we assumed that that was close to a 2-year event. So we ran our hydraulic model with a 2-year event and kind of compared what was going on. So I want to show you that. So first thing we noted here is that the road just is starting to overtop during that flood. Didn't quite get over the road, but it was close. And our model results here, this is where the road would overtop. Our water surfaces here that we computed for that 2-year event were very close to the top of the road. So that was really cool. Next thing we noticed here in this photograph is that this is standing on the south bridge looking north towards the north bridge back by that sign there. We noticed that in the photographs that water is flowing from the north bridge along the upstream embankment here and then going under the south bridge. And that's something you wouldn't guess with a one-dimensional model, but that is precisely what our model is showing here. Here's the north bridge, and you can see these flow vectors that the model's computing. It's showing flow running from here to here. So actually the water levels are higher here. Water runs across the floodplain in front of the embankment and goes under the south bridge. And then finally, this is standing on the south bridge on the downstream face, and that's looking south towards the floodplain to the left of the channel there. And that's right here in the model domain. So what you're looking at is water going under the bridge, and then it's overtopping the bank and spilling out into the floodplain to the south of where it goes under the bridge. And that's exactly what you see here in this photograph. It's almost a right angle where the flow is overtopping that bank. So not a hard and fast calibration, but this was really cool that this model showed all of this. And honestly, it's not something, if we were trying to model this in one dimensions, we would not be able to guess with that kind of precision that that's what was going on. So that was really great. So now, looking at, so we've got our model verified to the extent we could. So we ran it over a series of flows, and this is the results for the 2-year through the 100-year event. It shows how much flow was going through each bridge opening, which would have been somewhat of a guess with a one-dimensional model. The two-dimensional model is giving us a much better predicted result on that. And it's also telling us how much water is going over the road. So I won't belabor those points, but you can see here during a 100-year flood, there's a substantial amount of flow that goes over the road itself. And we're going to have to deal with that 600 CFS somehow if we're going to raise this road up and it's not going to overtop for our 100-year event. Okay, so here's just the model domain for the 100-year event. And the model is showing that there is substantial overtopping here, and notice that it's all north of the North Bridge. So the road is raised up above the floodplain here, but all the flooding occurs out here. And that seems to correlate with observations that we've gotten from the county. Okay, so let's now move on to the design. So the objectives now are we want to pass the 100-year event with overtopping. We don't want to increase flooding upstream. That's another constraint. And we don't want to change hydraulic conditions significantly. When we get into the design here, one of the objectives here is the county wanted to use the same bridge foundations. So basically, they're going to remove the existing bridge superstructures and raise the road, and then they're going to keep the bridge abutments, raise the road up, and then rebuild the bridge on top of the existing abutments. So the two bridges, the spans are going to stay the same. So important consideration here is we don't want to force too much flow through those small openings that would create more scour under those small bridge openings. Okay, so things to keep in mind. So what we did is we ran through an alternatives analysis, working with the county on this to look at various design alternatives. The first thing we did is let's just see what happens if we do raise the road. We raised it up 2 feet, and what we got was that the road overtopped that 2-foot higher road at the 50 and 100-year event. We basically created a bigger dam across the floodplain, so we created more flooding upstream, and we had higher velocities under the roads, more scour potential. So the idea was then we wanted to try to improve upon that. One little exercise we did is we wanted to see if we could get a little more flow through the South Bridge, just through some grading upstream, just due to the configuration of the floodplain and some existing berms along the channel upstream. So we did that. We didn't get a whole lot of benefit from that. It helped a little bit, but not a lot. So really the conclusion was here, we're not going to get to our design objectives by just using those 2 small bridge openings. We need more conveyance through the road crossing. And the solution was to add culverts to the road crossing. And so what we did is we started with a 12-foot by 3-foot box culvert placed along the road north of the North Bridge at the location where the road overtops naturally. And actually a single 12 by 3 box actually was large enough in theory to pass the 100-year flood without road overtopping. However, what we found in that analysis, we were increasing upstream flooding, which was not good, and we were also getting substantially higher flows through the 2 bridges, and hence higher velocities and shear stresses. So that led to really our final preferred alternative here. So we raised the road an average of 2 feet, but it varied 1 to 3 feet across the floodplain. The openings at the bridges were made larger just by simply raising the roads up. The bridge spans were the same. We did do some grading at the bridges to open up those constricted waterway openings at the bridges. And that included creating an overflow channel downstream of the South Bridge, where now there's a wall of vegetation at that location. And then we ended up with 2 12 by 4 box culverts through the roadway north of the North Bridge to mitigate for the raised road and capture that flow that would go over the road otherwise. And then there was a little grading downstream of those culverts as well. See, how am I doing on time here? Okay, I think we're doing well. Okay, so so here's what the design looks like. You know, we did some local grading at the crossings to open these up. The roadway here is raised an average of 2 feet. And then here's our two 12 by 4 box culverts in the floodplain, or in the roadway north of the North Bridge. Again, this is where you remember, this is where it naturally overtops. And then we have a little bit of grading downstream of that, those culverts there, and we've got an overflow channel to allow passage of flows downstream of the South Bridge. So that's kind of the overview of the design. So very quickly, of course, this was all analyzed in our two-dimensional model. To do this, we had to make some minor changes to the computational mesh to capture the changes at the bridges. We changed our, our roughness zones to reflect changes not only at the bridges, but where we're creating these overflow paths here. Otherwise, these roughness zones are the same as existing conditions. And then this is just a summary of the model results. A lot of numbers to stare at here, but I'll just point out briefly that if you compare at each bridge existing to proposed, what we're seeing here is roughly, particularly when you get around the 25 and the 50-year event, that these numbers kind of match existing roughly, particularly around the 50-year event. So we're not pushing a lot more flow through the bridge openings. And the culvert then is basically the goal here is where the culverts are overtaking where the water went over the road. The numbers don't match at all exactly, but this was the key to the project right here, is these culverts to mitigate for to removing the road overtopping, okay? And you can see here, by the time we get to the 100-year event, and we're capturing about 500 CFS with our culverts, where we had a little over 600 of road overtopping. So we're getting a little bit more flow through our two bridges, but because there's a little more waterway opening now with the higher bridge decks, that really wasn't a problem. So this was our design solution for this project. This is what the 100-year flow field looks like now. So basically, it's very, very similar to existing conditions overall. So we've got the similar flow patterns here at the two bridges. The model doesn't show the water going through the culvert in this view, but we've got the culverts about right there. So that's mitigating for or similar to what would have gone over the road itself. Otherwise, this flow field looks very similar to existing conditions. Okay, so we've got, we're meeting our objective of getting water under the road. Now, what about flooding? This site is in a FEMA Zone A. Since it's in a FEMA flood zone, special flood hazard area, we must meet local floodplain regulations, which are in Lane County Land Use Code 16.244 there. Because this is a proximate zone A, if you guys are familiar with floodplain regulations, there is no regulatory floodway up in this rural area, so we don't have to meet a strict no rise. However, FEMA guidelines for proximate zone A's, you can generally get away with up to a foot of water surface elevation increases. And so that was our absolute requirement, but the county, we really wanted to do much better than that. We really didn't want to substantially change flooding as part of this project. So this slide then compares 100-year water surface elevations. You can see in the legend over here, we've got small changes, both not negative and positive. The cooler tones are negative, the warm tones are positive. But you can see upstream of the bridge, actually we're reducing water levels, mostly small reductions between 0 and 1/10 of a foot. In some areas, it's a little more than 1/10 of a foot. So we actually reduce flooding upstream just a tiny bit. Downstream of the project, inherent because we're running a two-dimensional analysis and we've changed the distribution of the flows coming over and under the bridge, there are some small areas where we're getting some tiny increases. Generally less than 1/10 of a foot here, So really pretty darn good. And if you were to average these out across a transect, like you would typically do in a one-dimensional analysis for a flood type study, you know, really on average, we're not increasing flooding downstream either. So a very good result. So we're meeting the objective there with flooding and doing a really good job at that. And then finally, now let's think back to the other objectives of the modeling. We've got to design these crossings now for scour and for scour protection. So this is what the computed velocity field looks like for the 100-year flow. And you can see here that we got higher velocities underneath each bridge because we are still forcing flow through these narrower openings. Actually, the velocities aren't too bad. They're around 6 feet per second or so under the bridges. However, coming out of our culverts, this is the hot spot right here. We really have some really high velocities coming out of those culverts. So part of the design, we really needed to mitigate that so we didn't have a bunch of erosion and a big scour pole right there in the floodplain downstream of our new culverts. So let's just look here at the design. So the next step then in the design process is to compute scour. Okay, so that's what I'm going to talk about next. For you guys familiar with hydraulic design of bridges, computing scour is the guidelines come from the Federal Highway Administration. That's what ODOT follows in their hydraulics manual. And the scour is really outlined in the Federal Highway Administration document HEC 18. Gives the federal guidelines on how to compute scour. And if you're familiar with scour calculations, the calculations are broken into different components. You have what's happening with the overall stream. Is the stream cutting down or grading, et cetera? That's known as long-term degradation. That's why early in the presentation, I was talking about channel stability, because we need to evaluate that because it actually becomes part of our calculation of the potential scour depths at the bridge. And then we also computed what's known as general or contraction scour. This is the scour that occurs because we're taking all this floodplain flow and we're forcing it through a narrow opening. So these two bridges are still narrow openings compared to this big wide floodplain. So we're going to get some scour, mainly what's known as contraction scour. A final component of scour that is in HEC 18, if you're familiar with that, is what's known as local scour. But we didn't quantify that because the local scour is a scour that occurs due to turbulence because of an obstruction like a pier or an abutment. But we don't have any piers, so we don't have pier scour. We do, however, have the bridge abutment. So there is a potential for local turbulence around the abutments. But what we're doing, as you'll see in our scour design, we're putting in sloping riprap revetment or riprap around the abutments that's going to prevent that local turbulence from happening. So really, we only really need to be concerned with long-term degradation and general scour because the turbulence or the local scour is going to be protected by the riprap. So following ODOT and Federal Highway guidelines, we ran the 100 years, we did the calculations using the results from the 100-year event. And then because our road actually doesn't overtop during the 500-year either, the 500-year event becomes our scour check design. So we calculated scour for the 100-year and the 500-year. And these are just the different results at the two bridges here. So we've got, we're assuming now, based on our channel stability evaluation, that we don't see any long-term changes in the bed elevation that look like they're going to affect these bridges. So we assume the long-term degradation to equal 0. And then we have spreadsheets where we take output from the hydraulic models and input it into the scour equations. This gives us the contraction scour depths. And then you add these together to get the total scour. And I'll just make a note here that since we've got this two-dimensional model now, we can do a much better job at predicting scour because now we know those hydraulic variables with a lot better precision than when you would get out of a one-dimensional model. So we're taking the appropriate results out of the two-dimensional analysis and plug them into these scour equations, and it really gives you a much better result. And so based on this, we know the scour depths and we know the initial bed elevation under the bridge. This is basically the final general scour or contraction scour elevation that would be predicted during these big floods. And that then was used as part of our scour mitigation design. So let's quickly go through the design recommendations here. And I'll show you the designs at each bridge and what we did. So this is the North Bridge here. Blow up of that area. Again, the county is going to reuse the bridge foundations. So the span width is the same, about 60 feet. The roadway will get raised up, so the deck will be a little bit higher. And then, so what we did here is we did some local grading to improve the conveyance, so the connectivity of the waterway under the bridge with the channel upstream and downstream. And then this is the footprint of our proposed scour mitigation at this bridge. Again, currently the bridge is rated scour critical, and the county is going to reuse the existing bridge foundations. So, you know, as part of this project, they don't want to build a new highway and have the bridges still be scour critical. So we addressed that as part of this project with the scour mitigation, which is basically riprap revetment to protect the bridge foundations from that turbulence or that local scour. And so this is a cross-section view of the riprap revetments on the abutments, protecting the abutments from the scour. And the riprap then goes down now below the computed contraction scour. So there is still an active bed here in the middle of the channel. So that's why the contraction scour is computed to make sure that the revetment doesn't get undermined. So that's the scour design at the North Bridge. This is how we configured it in our report. Being mindful now of environmental compliance regulations. I'll just talk about that for a second here. Typically, when you're replacing rock in the stream, you've got to deal with environmental regulations. And for scour mitigation, they define what's called the active channel width, which is determined in the field. And then the environmental regulations usually prevent, for streamland permitting, prevent any kind of hardened material inside what they call the scour prism. So basically it's some multiple of the channel width or just equal to the channel width, depending on the jurisdiction. And then they look at the computed scour, the general scour, the contraction scour I showed you. That forms a rectangle here, which unfortunately I didn't draw on this figure, but basically the bottom of that rectangle is at the contraction scour elevation. The width is the active channel width or some multiple of that. As long as you could keep all of your rock revetment outside of that rectangle or what they call the scour prism, then you can meet the permitting requirements. So basically this rock now is down below the scour elevation and it should be wide enough to accommodate the channel width. And that will, I don't know where the county is with their final permitting. We weren't part of that, but their final design will make sure that rock is outside of that window. Okay, so just finishing up here, that's the North Bridge. The South Bridge now isn't on an active channel, and we ended up deciding actually to revet all the way across this opening. It was going to be less expensive. And also what we're doing here is we're filling in the existing scour hole underneath that bridge because we don't want to strand fish during a big flood. So what we did here is we filled that in with rock, graded it out in a way that there's an open pathway back to the main channel downstream so that we're not stranding fish, and there's a nice waterway opening there. So that's a cross-section view of that revetment. Just real quickly here, this is that grading that we did for that overflow path to allow an overflow channel downstream of the South Bridge, which actually kind of matches up with the sort of the natural overflow paths here in the floodplain upstream. So this actually could maybe help them with some environmental mitigation depending on how that process goes. And then finally, these are the box culverts that were used for the north, for the culverts upstream of the North Bridge, or I'm sorry, north of the North Bridge through the roadway opening there. And then this is the grading then downstream of those culverts. And you'll remember we had really high velocities coming out of these culverts. So what we suggested is they armor the overflow channel downstream of the culverts with something like Armor Flex, which can be actually, if you've seen these are like blocks that can be planted and the county could mow these, et cetera. And it would just blend in really nicely with the floodplain and the downstream of the bridge there. So that, ladies and gentlemen, is my presentation. And so I think, Jennifer, if you want to come back on, we can open it up to questions.
Great, thanks, Gary. So we had a couple of questions. The first one happened when you were talking about modeling, and Gary was asking about how I believe he's asking about the modeling, but how well is the hydraulics model coordinated with geotechnical? He talked about an experience of the hydraulic modelers sometimes saying they have critical scour when it's solid rock.
Okay, well, that's a really good question, and it's a big challenge that we often run into in these hydraulic design projects. See, the hydraulic engineers are predicting scour basically in most cases assuming that the material is erodible. Now there are some of the scour equations, particularly in the later versions of the Federal Highway guidelines, that will account for things like a large material, like coarser bed material in the scour calculations that will tend to limit the scour. And there's even some equations in there if you understand what the soil properties are and you've got very cohesive soils. If you know what the geotechnical properties of those soils are, mainly the critical shear stress, which is often a hard parameter to get at, the scour equations can take that into account. There is no easy way to account for bedrock. So typically what we should know about the geotechnical, and you're absolutely right that we should be working very closely with the other disciplines, with the geotechs and the structural folks. And if we've got bedrock, we want to know that because that may limit the scour. And if it's competent bedrock, that's great because that's going to limit the scour depths. I'm actually working on a project in Colorado right now where that's the case. We've got very competent sandstone down below the bridge foundation. Our computed scour depths are below that, but we're saying if you can protect down to that sandstone, it's good.
So the next question, so thanks, Gary. The next question is, how much influence do the dimensions of the computational mesh have on model results?
That's also a very good question. And luckily they're not super sensitive, but as you could see in the screenshot I had there of the computational mesh, we did make it a lot denser in the vicinity of the road crossing. There have been experiments to determine, what is the sensitivity to different size meshes. And one of the things that I do, if folks are interested, the Federal Highway Administration has webinars that occur about every 2 months on this type of modeling, on two-dimensional modeling, and it's run by a guy named Scott Hogan. He's one of the chief hydraulic engineers at Federal Highways. Actually, I used to work with Scott back in Colorado, but Scott has addressed that question where he's shown some simulations that they've done where they have a fine mesh and they've made it a lot bigger. And then luckily, the lucky thing is, if you've got a reasonably sized mesh, the results aren't that different. And it can make a huge difference in the run times. If you just blanket come in and make really small elements everywhere, the run times are going to kill you. And that's why, like I showed, we made the elements smaller next to the bridge. And there's some guidance on kind of, what's a reasonable size. And we kind of followed that. And I feel pretty confident we have a good result. So.
Thanks. So that is a pretty good transition into the next question from Seth. Could you recommend a good training resource for SRH2D or those familiar with HEC-RAS 1D?
Okay. SRH2D, the training currently is being done by the Federal Highway Administration. So go to the National Highway Institute website and they'll list trainings. And, you know, historically they've done those live. There were, last year, there were a couple right here in this region. There was one up in Vancouver, and I think they were up in Olympia as well. Because of COVID, right now they're not doing that, but they are doing, they're doing this online now. So go to the Federal Highway Administration's website and look for those trainings.
Great. And I also have a question here about what about low flow sedimentation deposit issues?
Okay, well, that's a good question. First of all, I'm not too worried about low flow sedimentation for this particular stream. This is a very cohesive soil in the stream. There's not much bed load. And the existing, as you saw in the photographs, the existing bridges actually are scoured out underneath the bridges. There really isn't much of a sedimentation issue there. We did, as part of this project, look at the hydraulic results very carefully, comparing existing to proposed. And that's why, again, understanding the existing characteristics of the stream is very important. There really is no obvious sedimentation issues with this stream. It's basically what we would call a threshold stream. It's mainly, there is some fine material in there, but it's not a dominant bed load transport stream. So honestly, sedimentation is not going to be an issue with these bridges, and we've made the waterways similar, maybe a slight improvement from existing conditions where there are no sedimentation issues.
Great. So we also have a question from Gregory Savage. Gregory, if you're there, I'm going to go
Greg.
ahead and
I know Greg.
I'm going to unmute your computer. Go ahead, Gregory. Oh, you have to unmute yourself now too.
Hi there. I actually didn't have an immediate question. I was just fiddling around finding out how to use the controls. Whoopsie.
Well, perfect. So everybody can see too that you can also raise your hand, your virtual hand in the webinar and ask questions that way as well.
I'm intrigued by,
oh,
no,
and I
real
was
quick,
also going to just say, people, there's also an option that I can, if you want to expand on your question or the answer didn't fully answer your question, go ahead and raise your hand, and that way I can easily find you in this list of participants. But go ahead, Gregory.
I'm intrigued by the fact that, you know, I'm up in Portland and we have lots of flood regulation, and I'm intrigued by the completely different world down there in terms of requirements.
Well, this was an approximate zone A.
Yeah.
So there is no strict no rise, and I don't even think that would be true in Portland.
Yeah.
Because it's not a floodway. So we're in a very rural setting here. So that's why the floodplain regulations, by the fact that there's no floodway, are probably a little more relaxed. But we essentially met a no rise on this project. If we ran a one-dimensional model, I think you would see that. And I'll just comment really quickly here that the floodplain regulations are trying to catch up with advances in the modeling. The regulations were kind of written in a one-dimensional world where you have one water surface at each cross-section, and that's the no rise. You can't have a rise there. Now with two-dimensional modeling, we're computing a water surface everywhere, and it's if we had to meet a 0.00 change at every location, we would never get there. And I know FEMA is grappling with that right now, and they're trying to come up with ways to maybe calculate an average water surface on a transect or something.
I think that, you know, when you have any change in geometry necessitates a change in response, and that includes water surface elevation. And, you know, flood risk needs to be looked at in terms of impacts, not just simply what the water surface elevation change is.
Yeah.
And I hope that gets adopted, and that kind of risk based thinking gets adopted in FEMA thinking.
Yep, that would be good. They're working on it.
Yeah.
Let me go on to the next question. And when
Sure.
I'm getting a rabbit hole with talking about FEMA, that could go on forever.
All right, thanks, Gregory. So John asks, what is the estimated construction cost for this project?
That's a good question, and I have no idea. First of all, we were looking just at the hydraulic design of the bridges, and there's a lot more elements to this project than what we were looking at. I don't know if my client is on the phone and would want to answer that, but I am not in a position. I can tell you what our fees were, and that's about it.
So if somebody is on the webinar who is with Lane County, who knows that answer, or the engineering team, go ahead and raise your hand, and then that way I can easily find you, and I can unmute your computer or unmute you for the webinar. I'm not seeing anybody, Gary.
Okay. All right. Sorry, folks. I don't have an answer for that, and while I like to be well integrated with the overall team and the project, I just wasn't. I don't know what that number is. Actually, what I'd suggest, I think the county has some information on this particular Territorial Highway project on their website, so you might look there.
So a couple more questions. Questions are still coming in. And just to let people know, it wasn't probably very clear. I just updated the chapter website for this, but I've scheduled all these webinars from noon to 1:30. So I know a lot of people had to drop off at 1 o'clock, but hopefully in the future webinars, it'll be a little bit more clear for people. Andy asks, as a result of the project design, is there any recommendation for ongoing vegetation management upstream or downstream of the bridges and culvert?
The answer is no, that I'm aware of. You know, it's a pretty rural, natural setting. Our analysis did factor in the very rough condition of that channel, particularly upstream. So, you know, there's no direct, as far as I know, there's no direct desire to go in and clear out that channel. We designed the project to work with that existing vegetation. Now, certainly right at the crossings themselves, the county should, and I'm sure will, maintain the waterway openings right at the new bridges and the culvert, but up, you know, well up and downstream, I don't think there's any plan to do that.
So there's also a question of how far off are we from 3D that would be even more helpful?
Yeah, I think three-dimensional modeling is a reality. It's out there. The computational requirements are even that much more onerous in terms of run times, et cetera, and data. And honestly, for this kind of project, since flow is predominantly in 2 dimensions, I think the 2-dimensional modeling is really sufficient to do what we need to do. 3-dimensional modeling is out there, and it's used now is more specialized for things like what's happening to, it's more environmental, like what's happening right at an outfall from a hydropower plant or something that's putting in hot water into the stream. And we want to understand what the dispersion of that water is, or a pollutant, that kind of thing. That's where I understand 3-dimensional modeling is being used right now, but I don't see it in my career happening for projects like this.
So I do have Maria from Lane County on the line here. She raised her hand to talk about some of the floodplain restoration downstream of the project. Maria, if you can unmute. Hi.
Hey, Maria.
Hi, I'm here. I can speak to some of the floodplain restoration work we're planning on doing downstream. We will be doing some vegetation management and some restoration, putting in some wood habitat structures, that kind of thing downstream.
Yeah, that's great. It's a beautiful setting out here. So you know, doing a little restoration of this site is pretty exciting.
Yeah, it's nice to be able to add a little extra onto there.
Thank you.
Thanks, Maria.
So there are not any other questions. Let me just double check the chat box here. William Solowata from Lane County in the chat box said that the project is estimated at $3.34 million. And then Gary also has a question about how is the riprap placed below the bridge? Is the existing bridge superstructures being removed and replaced higher on the existing piles?
Yeah, so the existing bridge superstructures will be removed as part of this project because the county is raising the road up and they're going to build a new, you know, superstructure across these. So I'm sure that that would facilitate the placement of the riprap, which is pretty tight under there.
All right, so there are not any more questions here. So again, thank you, Gary, for being the first one in our new Lunch and Learn series. And this was a really educational and interesting project. Just to go ahead and remind people, I will.
Do you want to take back control or anything?
Yeah.
Stop share. There we go.
So here are the upcoming sessions. And like I said, I've scheduled them all from noon to 1:30. You can go register at the Oregon chapter website for future sessions. And I usually post that registration about a month ahead of time. So they're up there and ready to go. And again, I just want to thank you, Gary, and everybody else. We had a great turnout today, and I look forward to talking to everybody in the future.
Thanks a lot, Jennifer, and thanks everyone. This was really fun.
Yeah, thank you.
Bye.
Bye.